All right, good afternoon, everybody. We'll go ahead and get started with today's webinar. Today we're talking about Wi-Fi. We're not going to talk a lot about products. We're just going to sort of talk about, how Wi-Fi works. We still find in this day and age there's a lot of people that don't really understand Wi-Fi, including people that have been selling it and dealing with it for years and years and years. It is a bit confusing. It's something you can't see, you can't smell. Um, but you know when it's working and you know when it's not, but you don't always know why. So we'll talk a little bit about some of that. We'll talk about some best practices. We'll talk about some of the new technologies that are coming along or have just recently launched here in Wi-Fi. As we go through today, if you have any questions, feel free to ask them, but I want you to do it using the question and answer interface in Zoom. Do not send it in via chat because I can't see those easily. I have to pull up a menu and stuff like that. I've only got limited screen space here. Also, I'd like to apologize in advance for any background noise you hear. My office window is overlooking an area that it's having construction done today. So every now and then you may hear the sounds of a saw going off or people hammering. So I do apologize for that. So without further ado, we'll go ahead and get started. I'll just start here first off with just a quick background slide on Zyxel. For those of you that aren't that familiar with us, some of our newer partners. Um, so Zyxel has been around for 30 years, more than 30 years, making networking equipment. We were founded all the way back in 1989, with our main goal as being providing connectivity for ISPs and bulletin board systems back in the days, also doing business class data fax modems. To this day, still we sell a awful lot of modems. Just now these days it's VDSL and ADSL and stuff like that. Um, we have over 100 million devices we've deployed out in the field. The US office is based out of Anaheim, California. That is our sales, that is our marketing, that is our warehouse, and that is also our tech support. So when you do call in to get support, you are talking to a Zyxel employee, not an outsourced call center, and someone based here in California. These days, due to COVID, most of the reps are working from home. But once that finally clears up, they'll be back there in the office in Anaheim. So now on to Wi-Fi. So let's start talking about some RF basics. So there's three main names you're going to hear out there when you're talking about Wi-Fi and how it comes to be. The most important is the IEEE. What is it? The International Engineers and Electronics something engineers. It's like International Electronics something engineers. I'm sorry, I've completely, my mind's gone blank on what it stands for. But anyways, these are the guys who create the standards for all sorts of cool stuff when it comes to computer networking, and that includes Wi-Fi. So when you look at Wi-Fi products, you'll often see them described as 11N, 11AC, or 802.11n, 11.2.11ac. That is the standard created by IEEE that the product is based on. So the Wi-Fi Alliance is a group primarily of hardware manufacturers like Zyxel that came together to solve primarily one issue, which was compatibility. Especially in the early days of Wi-Fi, there was problems with one vendor's 802.11a product not working with another vendor's 802.11.a product because there was no one out there enforcing the standards put together by IEEE, and even the best written, standards still leave room for things that may be up to interpretation. It says to do this, but somebody may interpret it differently than somebody else. So Wi-Fi came together, and these started testing and certifying products for compatibility. So in order to have a product have a Wi-Fi logo on it, they must have passed certification by the Wi-Fi Alliance. The Wi-Fi Alliance also helps to sort of market the technology, and they're the ones behind the recent change from describing products as 11N, 11AC, 11AX to referring to them as Wi-Fi 4, Wi-Fi 5, Wi-Fi 6, just to try to make it that much friendlier and make it clearer which is the newer technology. And then last but not least is the federal government with the FCC. The FCC basically determines which channels can be used for Wi-Fi without a license. They can determine things like how strong your signals can be, how much bleed over can be, things like that. So those three are what you're going to see all combined together there. Now, I will add here that when it comes to products being certified with that Wi-Fi logo, it's generally going to be just on consumer equipment. From what I'm seeing, most business class products don't bother with the Wi-Fi Alliance certification. So we'll talk a little bit about radio waves. We call them waves, not just because on an oscilloscope they look sort of the same going up and down as water waves, but in many ways they behave the exact same way or very similar to actual physical waves you would see in a pond or something like that. And as we go through today's presentation, I'm going to use that analogy several times. So just as a general rule, as frequency goes up, the more data that can be encoded on it. But also as frequency goes up, the lower and shorter the range. For those of you that are old like me, you'll remember the good old 900 megahertz, or maybe even some cases, I think 700 megahertz cordless phones back in the day. Those things were great as a kid because you could get on the phone and you could literally walk over to your friend's house across the street and maintain a phone call. And then as technology got better and better and they went up to higher and higher frequencies, what happened, right? Sound quality got better. I mean, sound quality on today's, 5 gigahertz cordless phone is fantastic, but the range is significantly less. If you've got a big house, you may have to have repeaters in your house to be able to get full coverage everywhere. You may not be able to even use it out on your own lawn, depending on where your phone is in relationship to the headset. So in general, in order to broadcast radio waves, the FCC requires that you have a license to show that you're playing nice, you understand the rules and the behaviors and what you need to do with those frequencies. But they have opened up chunks of spectrum that basically anybody can use without a license. So as you can see here, we've got a little tiny chunk of spectrum down here at 900 megahertz, basically 26 megahertz in size. So that was, cordless phones were using those back in the days. And then they moved to 2.4 was opened up. So that gets us somewhere in the neighborhood of around 60 megahertz of usable frequency. And then we've got the 5 gigahertz spectrum. So as you notice, 5 gigahertz is much bigger than 2.4 and 900. So you can fit more devices into 5 gigahertz than you could in 900 or 2.4 without interfering with each other. But the trade-off is you get lower range. So you're going to find the power output of products, how strong those radio waves are, measured in one of two ways. You will either see them denoted as dBm, or you will see it denoted as milliwatts. Generally, you see milliwatts used more on consumer type products, and you see dBm used more on business class products. And part of the reason for that is, one, milliwatts is much more impressive. As you can see here, 20 dBm equals 100 milliwatts. 23 dBm equals 200 milliwatts. So obviously, if you're trying to make yourself sound better than your competitor, it's much more impressive to go from 100 to 200 as far as your signal strength than it is to go from 20 to 23. So when it comes to marketing stuff, particularly at consumers, that's where things go. When it comes to business stuff, generally most vendors realize that professionals are probably going to know the difference and aren't going to be easily fooled by the milliwatt thing. But also more importantly, if you're doing engineering and stuff like that, you will see that things like signal strength, antenna gain, path loss, all of those are going to be measured in either dBm or dBi. And so you can easily add that all together to figure out your total stuff. So you can take your 20 dBm radio output power, you can add in, 2 dB gain due to an amplifier, you can subtract out a 3 dB loss due to wiring, and then you can add in a 12 dBi gain due to an antenna that it's connecting to, and be able to easily calculate your overall total output power. Then you can always convert it back to milliwatts if you would like to. Another thing to talk about here is, even though you may be doubling power, and you are doubling power when you go from 20 to 23 or from 100 to 200 here in milliwatts, your range isn't doubling. It's nowhere close to that. There's a lot that goes into it, but just in general, wireless signal drops off quite quickly with distance. And I'll put up the formula here in a couple slides. Um, it's a complex formula. So some other stuff to know here. One of the probably the most overlooked things when it comes to Wi-Fi performance and testing out and analyzing your deployments is signal to noise ratio. So this is basically telling you the signal, which is the data that's being transmitted that you want to hear, versus the noise, which is basically everything else that's using that RF spectrum that isn't what you want to hear. It can be background noise, it can be other access points, other wireless devices, industrial equipment, whatever it happens to be. And that signal to noise ratio is the key determiner for just how fast and how reliable your signal is. So you could have a strong signal and be very close to your AP and still get very poor performance because there's a lot of RF noise, so you don't have a good signal to noise ratio. And then oppositely, you could be a long ways away from your access point, not have the strongest signal, but there's no noise. So you'll get a nice, fast, solid connection. Another term you'll see used is attenuation. Basically, how much that signal is degrading. So it's going to degrade as it passes through things. So that's things like you and me, walls, office furniture, but it's also just the air itself. So up here on the top of the slide, we've got here the formula for calculating your Wi-Fi distance. So if you want to know your distance between 2 points, this is the formula you would use here. But basically, this is just showing here on the bottom here, how much things are going to affect the dB of the product, right? So as the signal passes through a window, I should say here, this is the calculation for going through open air. So going through a window will get you about a 3 dB loss. So you're having the power, but you're only taking about 30% off of the effective range. A tinted window, something with a metal coating, that can take you down to almost as much as an 8 dB loss. Throwing on window screens will also dramatically reduce the ability of the signal to go through. As you see here, as you get thicker and thicker walls and floors, the more and more loss you're going to have as the signal tries to pass through it. So when it comes to signal range, we'll often get that question. If I buy your access point, what sort of range am I getting? And the challenge with that is it's really hard to be able to say because so many different things contribute to the performance here. So, Wi-Fi range is a combination of your signal strength. How strong is the signal that you're hearing? The signal to noise ratio, how much noise is there that's blocking it out? Attenuation, how much is the signal dropping over that distance? What sort of things are in the way that may be absorbing and degrading that signal? And then the frequency being used. So for instance, 2.4 will in general travel further than a 5 gigahertz. So that's going to affect things. Also, 2.4 is super easily absorbed by water, right? So microwaves use 2.4 radio waves to heat up food because of just how much water loves to absorb that 2.4 signal. So if you're someplace where it's humid, you're going to have less range than if you're out in the California desert where there is no humidity. And this is actually a problem we have run into in places like Florida and Alabama, where people are doing outdoor links between buildings. They'll set up the link during the day, and it will be fantastic. And then in the evening, a big heavy thunderstorm, clouds will move in. There won't be any rain, but the humidity will shoot way up, and suddenly that signal doesn't work anymore because the air is now absorbing too much of the signal due to the water in it. The other important thing to keep in mind here is Wi-Fi is two-way communication. So range is basically going to be established by the weakest member. So it's really normal to have an access point with 500 milliwatts, 1 watt, or even more power being broadcast out of it. So it can send that signal really, really far. However, your iPhone, your little cheap Amazon tablet, they're going to have oftentimes less than 50 milliwatts of signal strength coming back. So you're limited basically by that. So your phone, we'll say here, can hear the access point going really far distance from that access point. However, the access point can't hear the signal coming back from your phone, so your connection doesn't work. And that's something that leads to a lot of frustration that we've heard from people when we talk to people about Wi-Fi. Is they'll look at their phone and the phone will show they've got 2 or 3 bars of signal strength, but their Wi-Fi isn't working. And that's often the reason, because your phone is telling you how strong the signal is that it hears from the access point. It's not telling you whether it can send the signal all the way back to the AP. So oftentimes you've got, because of that power mismatch, your phone thinks it's got a reasonable strength signal. Unfortunately, the access point that you're connecting back to can't hear what's being transmitted back to it. So, a good way to sort of put this is to sort of think of like being, um, in a nightclub or something like that, right? If you're having a conversation, you're on a dinner date, you're talking to your date, right? When it's early in the evening, there's not a lot of people there, you can talk at normal volume and you're going to be able to hear each other just fine. But as we increase the noise, the signal to noise ratio, right? So as more people come in and these start talking, maybe the band starts playing, you now have to raise your voice to be able to hear each other. If you continue talking at the normal tone of voice, you're not going to be able to hear each other, right? And some points it gets to the ridiculous point where you literally have to be shouting into each other's ears to hear each other. So that's sort of the same thing there. It's another analogy here for the overlap here is, let's say one person's got laryngitis, they cannot speak loudly, and the other person has a normal voice and they can shout, right? As you move further and further away, only one side's going to be able to hear the other, because the other person can't shout back at the same volume for the other person to hear them. So some of the stuff that goes on with RF, again, RF, these radio waves, we can't see them, but they do have different behaviors. So as we talked about before, as you transmit the signal, it can pass through physical objects, although the signal is going to be weakened as it goes through. Depending on the angle and what the material is made of, RF can bounce off of stuff. So it can go around something and hit it and bounce off and go in another direction. Similar to, you can get sort of like an echo effect, but with RF, just like, sound will bounce off of walls and stuff in an empty room. It's just drywall and concrete, and you can get echoes pretty easily. It's the same thing with RF. It can bounce off and create sort of RF echoes. You can also sort of scatter the signal, where the signal hits something and then reflects off in multiple different directions. And it can also wrap around physical objects. So if you've ever been out and had a pond and thrown a rock in it, and there's a little dock out there, you can watch the waves hit the pole of supporting the dock and watch as they sort of wrap around it. Same thing happens with RF. So with the exception of Wi-Fi 6, this is how airtime utilization works. So with Wi-Fi, only one device can transmit at a time in general. There are some exceptions to that we'll talk about a little bit later, Wi-Fi 6 being a big one. But basically, the way this was originally intended to work back in the late 1990s, when the original IEEE spec came out, was that basically a device will listen when it needs to send something, and it will see if anybody else is broadcasting. If it doesn't see anybody broadcasting, it will go ahead and send the data that it wants to send. If it sees somebody else is broadcasting, it will back off, and there's a little random time generator for how long to wait. And then it'll check again to see, okay, is it my turn to send? And this worked perfectly fine in the early days of Wi-Fi because it was low data rate. Most people were doing stuff like that didn't need to be real time. It was okay if things got delayed a little bit. And unfortunately, until Wi-Fi 6 came about, so even with your 11 AC products, they're still using this behavior to determine when it's okay to send. So you run into a couple problems. The first one is, now we're doing a lot more data. We're streaming things. We're not just checking email and loading web pages. We're nonstop streaming high bit rate video. We've got a lot of devices using the airtime. We're trying to do voice, which doesn't use a lot of bandwidth, but is very, very sensitive to packets being dropped or packets being received out of order or delays on when the packets get there. So the way we use Wi-Fi has changed, and that's caused problems with Wi-Fi performance. Another problem we run into is we're using a lot more devices now, and you run into something here called the hidden node problem. So basically, you've got your access point in the middle of the slide here, and then in either direction, you've got a client that is talking to the access point. Yeah, and so the problem you run into is each client device can see the access point. So they know when the access point is broadcasting. So they can say, okay, the AP is broadcasting. I should wait for it to stop before I send my frames. But the client devices cannot see each other. So they're within range of the AP, but they're not within range of each other as far as they can visually see. So it's very possible as you increase the number of devices or you increase the amount of traffic being sent, that two or more devices will listen, not hear each other, and decide to transmit at the same time. And unfortunately, the AP can hear both. So it will have basically equivalent of two people shouting at it at the same time, and it won't be able to hear either of them or make sense of what they're trying to say because it doesn't know who to listen to, and the packets will get dropped. So this is one of the issues that you run into a lot with denser deployments and why Wi-Fi performance drops quite a bit. So another thing I want to talk about is data rate versus throughput. Um, these are not firmly defined terms. I'm trying to define them here as how you most likely are going to see them used out in the real world. So data rate is what you will see advertised on every vendor's Wi-Fi product. It is the IEEE standard for defining how much data is being sent between two devices. You will also sometimes see this referred to as a physical rate or the link rate. And the important thing here is that this includes not just the data you want to send, but it includes all of the protocol overhead and Wi-Fi overhead as well. So what you will normally see when people do a speed test, right? They'll go to speedtest.net or they'll send an FTP file between devices and then measure how much data gets sent. So we're going to call that throughput, and it's different than the data rate because it's only measuring how quickly you can send the data you want to send, and ignores a lot of the overhead. So because of that, we run into problems where people will buy a product, run a speed test on it and say, hey, you guys said it was this speed, but no, I can't get anywhere near that speed. You guys are liars. It's a cause of a lot of confusion and a lot of negative reviews, especially if you read Amazon reviews of any sort of Wi-Fi or power line type product. And the reason for that is something like Ethernet has almost no overhead. Ethernet has a ridiculously tiny amount of overhead, but something like Wi-Fi, which is broadcasting in the shared Wi-Fi spectrum, that wasn't really designed for sending data. The Wi-Fi protocol itself adds a ton of overhead and error checking and stuff like that. Um, so you'll see somewhere between 40 and 60% difference in throughput versus the advertised data rate. And that's why, because your throughput is ignoring all of this extra overhead that doesn't exist with something like wired Ethernet. So now we'll talk about increasing speed. So one of the main differences that gets promoted as each new Wi-Fi technology comes out is the faster overall speed. So I'm going to talk about how we get faster speeds in general from the technology standpoint of things, not how you would do it in the real world, with positioning devices and things like that. So the three main ways that speeds have been increased as Wi-Fi technology changes have been these right here. Increase the amount of encoding basically that's being done on those radio waves. So 11N use 64-bit QAM, 11AC uses 256 QAM, 11AX Wi-Fi 6 uses 1024 QAM in theory. Now, in order to be able to use these higher data rates or these higher encoding rates, two things need to happen. One is the chips need to have the horsepower to do this extra level of encoding. And that's always a problem with Wi-Fi, right? Because you're talking about this needs to be done on both sides, and one side is almost always a device that's running off of a battery. So you need to have really efficient yet powerful chips to be able to do the encoding. The other thing that goes along with this encoding is you need to have a really good signal to noise ratio. If you don't have a good quality signal, it will automatically drop down to these lower QAM settings. The next thing you can do is increase spatial streams, and we'll talk a little bit more about what spatial streams are here in a little bit. Spatial streams are something that really came of age when it comes to 11AC and now Wi-Fi 6. And the other way you do it is increasing bandwidth. 11G supported 20 megahertz channels. 11N gave you the option to use 40 megahertz channels. And 11AC gave you 80 megahertz channels. Now with 11AC Wave 2 and Wi-Fi 6, you get 160 megahertz channels. So we'll start by talking a little bit here about increasing the bandwidth being used, because you run into some problems. So one of the problems we run into here is that 2.4 doesn't have a lot of spectrum available. So you will notice here, here is our spectrum that's available. In the US, we have 1 through 11 available for us to use. In Europe and in Japan, there's some other channels that may be available here. So you go, well, I've got 11 channels to choose from. Well, the problem is the channels are only spaced apart from each other by 5 megahertz, but you're actually using around 20 megahertz in actual real world utilization. So these channels overlap with each other. So in reality, when it comes to 2.4, you've only got 3 non-overlapping channels that you can use to do Wi-Fi. So as soon as you add a 4th device using 2.4, you're going to start running into issues. And because of how powerful your AP is, you know, that interference can be coming from an access point that's quite a long ways away. It could be in your neighbor's house, in a business building. It can be up a floor or two. You could be surprised. And of course, you're sharing 2.4 with all sorts of other wireless devices, Bluetooth, game controllers, things like that. So one of the ways we boosted speed with 11N is we said, hey, you can use 40 megahertz channels, which is fantastic, except again, you've only got 60 megahertz available. So as soon as you add in a second device trying to use 40 megahertz channels, you've got interference. And in fact, the way the 40 megahertz works is they normally allocate that from the middle of the available spectrum. So even if you add a second 20 megahertz device, it will overlap and cause interference. So the way that these, tried to address this was moving to 5 gigahertz, right? The challenge was, well, your range is less, but you've got all these channels to use. There's something like 26 non-overlapping 20 megahertz channels. That's fantastic, right? So yes and no. So obviously you've got the caveat there that, you know, the range is going to be a little bit less, but you'll also notice on our little chart here, we've got this huge section in the middle of these channels that's highlighted in sort of an orangey color. So these are called DFS channels. So the trick was when the FCC decided to open up 5 gigahertz, is that there were already licensed users of 5 gigahertz space. The biggest one being radar systems, whether we're talking radar, weather radar, you know, airport radar, military radar. 5 gigahertz has primarily been used by radar systems. And obviously the FCC isn't going to go out there and force radar to somehow switch to different frequencies. So what they did is they came up with a rule that basically says in order for a Wi-Fi device to use a 5 gigahertz channel, it must check, and it has to check for a certain period of time, that that channel is not being used by a legacy licensed user. And only then can you broadcast. And on top of that, should you be using that channel and should a legacy user of 5 gigahertz decide to use that channel, you must stop using that channel immediately and either wait for them to stop or to find another channel. So because of that, 5 gigahertz DFS channels may not be all that stable, right? So they may detect either correctly or falsely that there's something else using the 5 gigahertz, and so they'll disconnect your users to switch channels. And if they're switching channels to another DFS channel, it's going to take a little while because they've got to check and verify this new channel is not currently being used. So oftentimes this causes complaints. We've had situations where industrial equipment is putting off 5 gigahertz RF that's being misidentified as a legacy user. So it causes disconnects from that, even if there are no actual, legacy users nearby. Um, Another problem that comes with using these DFS channels is in order to get your FCC certification that supports DFS, it adds in general up to 6 months to the certification process. So what you find is most business class products support DFS. Um, and they may ship without support, but support will be added via firmware. Whereas a lot of consumer equipment just doesn't bother at all. They don't want to wait 6 months. They need to be first to market, get that first mover advantage. And you can't trust end users to upgrade their firmware. So they'll just simply ship the product without DFS support and may never add it. So what happens is you run into situations where you've got your corporate networks on a DFS channel, and people bringing equipment from home aren't able to connect because their cheap Walmart laptop or their inexpensive Android phone doesn't support DFS channels, so they can't get on the corporate network. So because of that, a lot of people choose to just not use those channels at all. So now you've gone from 26 non-overlapping 20 megahertz channels down to like 9. And again, of course, the reason we're talking about all of this is because we're talking about increasing overall Wi-Fi speed. And one of the main ways you do that is by increasing the bandwidth you use at a time. So if you jump up to 40 megahertz channels, right, you've now only got 4 non-overlapping, non-DFS channels to choose from. But of course, we want faster and faster speeds. So we decided to start using 80 megahertz channels. So now you've only got 2 available without dipping into your DFS channels. If you dip into DFS, you've got a little bit better there. And then of course, the new thing here is 160 megahertz channels to make those really, really fast speed claims. So those do have to use DFS channels. There is no way to avoid it. So now let's talk about spatial streams. We kind of sort of touched on this in the slide where we were talking about RF behavior. So one of the things that used to be the bane of Wi-Fi back in the days of 11B, 11G, and even 11N was this thing called multipath. You would sit here and you would transmit your signal. It radiates out like a wave from the transmitter, and it's going to be hitting different objects in the environment at different times and then bouncing off of them in different directions. So what happens is sort of the same thing again. If you're talking to somebody in a room that's basically just concrete floors and drywall, is that when you talk, you get an echo. And that same thing happens with RF, and we're calling it multipath. Basically, because the signal is bouncing off of different objects and taking slightly different paths, because the lengths of those paths are different and variable, you get echo type effects of that data, and it could confuse the receiving side of things here. So this was a problem, and eventually some people who were smarter than me, including some people at our Zyxel chipset spinoff, came up with some technology that actually converts this problem of multipath into a net positive. And it gives us something that we call multipath, and allows us to turn that into MIMO, multiple in, multiple out. So technology got to the point where we can differentiate those echoes and recognize what is an echo, and that it's coming in at different times and not get confused by it. And then we took the technology and said, you know what we can do? We can take advantage of these different paths and use each path to send different data at the same time. So you have what's called MIMO here. So this is how you would get your faster speed. So each of these paths that the signal may take, we call a spatial stream. So and the way we know that there's going to be different timing and different paths taken is we will use different antennas placed specifically at a certain distance from each other to generate this sort of echoey effect. And then we're able to send different data on each one of these spatial streams. So for instance, base 11N supports 150 megabits of data. That's what you can transmit. Now, if you find a way to send a second stream at the same time, you've now got 2 150 megabit streams that can be combined together for 300 megabits total. So when you see a product on the consumer side that was advertised as 300N or N300, That's what it was telling you, was that they were using 2 spatial streams to get to that speed. You could have added a third spatial stream, and you can get up to a 450. And I think in some cases they even have products out there that support 4 spatial streams when you get an N600 product. It gets kind of confusing with 11AC and some of the later 11N stuff, because they'll start combining spatial streams from 2 different radios, right? You'll have a 2.4 and a 5 gigahertz radio in the same device, and so they'll combine those speeds together. But just in general, you can, with a single radio and multiple antennas, you can get up to 4 spatial streams going at once. So with 11AC Wave 2, they added something here new called multi-user MIMO. So here we were using multiple antennas to transmit different spatial streams, which would then be received by different antennas over here and combined together for one faster connection. With multi-user MIMO, instead of being transmitted to one user and combined together into one faster stream, you've now using these spatial streams to the AP to be able to send data to multiple client devices at the same time. So one spatial stream will go to one user, a different spatial stream will go to a different user. So this is great when you've got situations where your access point supports faster speed than your client devices, which is really common with phones and tablets. It's very common for an access point to support 2, 3, or 4 streams, but for a client device to only maybe support 1 or 2. So when you look at a data sheet for consumer products, you probably won't see spatial streams mentioned, but business class products pretty much always have the spatial streams listed on the spec sheet. And you will see it denoted as something like a 2x2 or 3x3. And oftentimes you will never see on business products, you won't see any sort of speed like N300, N600. You will only see references to 2x2, 3x3, etc. So basically this first number is telling you how many spatial streams your device can transmit. And the second number is telling you how many spatial streams your device is capable of receiving. On most access points and routers, it's going to be the same, 2x2, 3x3. But again, when you move over to mobile devices, client devices, it's very common for them to only be able to transmit, say, 1 spatial stream, but be able to receive 2 or more spatial streams. So they can receive a fast signal, but they can receive a lot of data, but they can't send as much data back to the access point. And some products, this is mostly these days done by Cisco and Meraki. You will see something here where it's denoted, like in this example, 4x4:3. So it's a little bit confusing because at first off, you think, wow, I've got an extra spatial stream versus a product that's 3x3. But the colon is actually telling you how many spatial streams can be handled at a time. So basically a 4x4:3 can only support 3 spatial streams, but it has 4 different antennas it can choose to use for those spatial streams. So you're only ever going to use 3 at once, but in theory, if one of those antennas doesn't have a very good signal, but the other 4th antenna has a better signal, it can switch to that 4th antenna. So it's supposed to help a little bit with coverage, but overall the net speed is still the same as a standard 3x3. So here's a little chart showing you how we get these speeds. So when you're looking at what's advertised on a product, it's always going to be the fastest that things support. So it's going to take the highest number of streams that are available on the device, the highest modulation it supports, and the largest channels it's going to be able to support. So for this case, a 3x3 device, this would be an 11AC device that supports 256 QAM, will be advertised as supporting, 2,600 megabits per second speed. So obviously, first problem you run into is, let's say you don't want to use 160 megahertz channels because you don't want to support DFS because you have users bringing their own devices from home that won't work with DFS. So now you're dropping your speed in half because you're going from 160 megahertz available to 80. So now your maximum speed realistically is only 1,300. And you've also got some signal noise issues, things like that. So most of your users aren't actually able to achieve 256 QAM. They can only do 64 QAM. So now the speed will drop here to 975. And most of your client devices aren't going to support, 3 spatial streams. Maybe it can only support 2 spatial streams. Now your speed's dropped all the way down to 866. So this comes back again to people's complaints when they do throughput testing compared to the speed advertised on the data sheet, the data rate, is it may very well be possible that either due to the environment or due to the client equipment they're using to test the speeds, or the channels they've chosen to use, that they aren't actually capable of using the fastest speeds that that product supports. It may be they only can use a slower speed because they don't support enough receive spatial streams. They don't want to use DFS channels, whatever it happens to be. So just something else to keep in mind as to why one device may not be getting the speeds that you would think it should be able to get based on the access point. So the next question that's super common for us is, okay, if I buy your access points, how many devices can I get in there? How many users can connect to this access point? And realistically, the answer is it has almost nothing to do with the access point. If you look at data sheets, they will list, a certain number of users that can connect, whatever it happens to be, 128, 256, 512. But that's not based on anything real world. That's basically just based on how much memory have they allocated to store association data for users. Realistically, in the real world, you're going to run into issues and your Wi-Fi network's going to be having issues long before you get anywhere close to whatever the maximum users is on the data sheet. And that just has to do with the way Wi-Fi works and the type of data that you are transmitting and using at a time. If you are doing voice over IP, so you're doing voice over Wi-Fi, you are going to need to keep a minimum number of users on there because of just how sensitive voice communication is to interruptions. Something like a high speed, high data video stream, like watching a movie, isn't going to be particularly sensitive to this because it can buffer. You can't buffer when you're doing voice communications because it adds too much delay to the communications and you end up stepping over each other all the time. And then just in general, as we talked about before, the way a Wi-Fi device determines if it can send or not is to listen. So as you add more devices, much more likely you're going to have the hidden node problem we talked about, and also just much more likely that 2 or more devices are going to listen and decide to transmit at the same time, even if they can see each other. So those sorts of things all sort of degrade what's going on. So it's really hard to say how many users your AP supports, but in general, it doesn't matter which AP hardware you're using. In general, it doesn't matter if you're using a $80 access point or a $600 access point. The AP isn't going to be your limitation. Just the way Wi-Fi itself behaves is going to be your limiting factor, and it's going to be the same on any device that's using that same technology. So here's a theoretical example, just showing you just by changing the device types, or in this case, how many spatial streams can be used, how it can dramatically affect the throughput and how many devices you can get on the network. So in this example here, we're taking devices, and these devices are doing a 3 megabit video stream. So they're watching a Netflix or YouTube video that's encoded at 3 megabits per second. You've got a nice fancy Dell laptop here that supports 3 spatial streams. You can get 34 laptops on that network, each doing a 3 megabit stream, and you will have no performance issues. Changing nothing else but switching from this high-end laptop to a tablet, which only supports 2 spatial streams, you've now cut the number of users down to 21. So you've now got 21 devices that can stream a video stream at 3 megabits per second due to airtime utilization, right? You can only transmit to one device at a time. Switching to something like a smartphone a cheap smartphone that only supports 1 spatial stream, you're now down to just 10 users on that same access point that can watch a 3 megabit stream before you're going to run into issues, because there's only so much airtime available. And because there's less spatial streams, less data can be sent at a time for each user. So you can see here aggregated throughput on laptops is 100 megabits, aggregated throughput on 2 spatial stream devices, 65 megabits, aggregated throughput on single spatial stream devices is just 30 megabits per second. And this is with watching something that's very easy. You start throwing in different types of devices with different signal strength, different data rates based on the signal strength, how far away they are from the access point, things like that. So you can see how dramatically just some minor things can shift the real world experiences on the same access point. So now I want to talk a little bit here about our smart antenna technology. This is something we offer. This is something Ruckus offers. It's called Smart Antenna. And we particularly promote this as a solution for co-channel interference. That's how we've optimized our the algorithm we use on the smart antenna. So let's talk a little bit about it. As I've mentioned before, in general, only one device can transmit at a time. Now, with something like MIMO on 11AC, the AP can transmit data to 2 devices at the same time. It's only it can transmit. No other devices can transmit back at that same time. So co-channel interference is this interference we run into anytime 2 or more devices try to use the same channel to send data. It doesn't have to be Wi-Fi. It can be any other source of RF noise. So general, when you're looking at your access points, they're designed to be mounted on a ceiling in the central area. So they radiate out an antenna pattern that's roughly a circle shape from the access point. Now, in the old days, the way you dealt with co-channel interference, and you still do with traditional fixed antenna APs, is you carefully plot out where you're going to place each of them. Maybe you buy an expensive tool that sort of tries to estimate how the signal is going to wrap around objects. You carefully plan which channels they're going to use, or you trust a wireless LAN controller to intelligently make those decisions for you. And then you drop the signal strength of your access points that are still overlapping to stop them from overlapping with each other. So it does stop co-channel interference. However, it lowers your signal to noise ratio because now the received signal that your client device is getting is much lower while the noise floor is staying the same. So you're solving the co-channel interference performance issues, but you may be, introducing signal to noise ratio performance issues. So the way smart antenna technology works is instead of having one fixed antenna pattern, you have the ability to use hundreds and hundreds of different antenna patterns. And in the case of our products, we optimize the algorithm to not only pay attention to focusing the beam, choosing an antenna pattern that focuses the coverage where the client device is, but also focuses on other sources of RF and tailors the signal to try to ignore those so the access point isn't hearing other sources of RF interference. Smart antenna technology is cool, because it works with any sort of client device. It does not require any special technology on the client device in order for it to work. And unlike beamforming, it also works with moving devices. So as a user or a mobile device moves around in the coverage area, we're able to, in essentially real time, change the antenna pattern to match them, which is something that doesn't work well with other sorts of technologies like beamforming, which try to do the same thing. So we've got a sort of a test scenario here. This is a hospitality environment. We took our product, an NWA 1302, and we took an equivalent Ubiquiti product, 5 gigahertz channels. And you can see we deployed multiple APs at 1 AP per room, which is really common these days in hospitality deployments. These are lower powered APs to try to reduce the bleed over from room to room. And we did some testing here. So the main difference between us and the Ubiquiti is the smart antenna. We have a smart antenna, Ubiquiti doesn't. So with 1 AP being turned on, you can see here performance was about the same. In fact, Ubiquiti slightly outperformed us. And airtime utilization in this example was 67%. So 67% of the available airtime was used to achieve these speeds. And this was done by simulating multiple clients connecting to each device. Then what we did is we turned on a second AP several rooms over that's using the same channel. And we see what happened here. Overall aggregated throughput went up. So Ubiquiti went up. Aggregated throughput went from 406 on 1 AP to 555 aggregated between the two access points that are turned on. But you'll notice due to our smart antenna technology, we were able to actually boost our speed a lot more, up to 785 megabits versus Ubiquity's 555. And if you look at airtime utilization, you will see the Ubiquity maxes out at 95% airtime utilization, which is good. But due to smart antenna technology, we can actually exceed 100% airtime utilization because smart antennas allowing multiple devices to transmit at the same time without interfering with each other by tailoring that RF signal to not cause interference. So you get actually 131% airtime utilization. Another thing you will notice is with smart antenna, the performance between the two APs is pretty equivalent to each other. Whereas with Ubiquity, you'll notice one AP is hogging up most of the available bandwidth and airtime. So now we do the same thing and we add a third access point. And again, you see here, the Ubiquity's aggregated throughput essentially stayed the same. And in fact, their airtime utilization went down because of the way Wi-Fi handles whose turn it is to transmit. It's not as efficient as it should be. But again, smart antenna allows us to jump up to 155% of available airtime, get over 900 megabits aggregated throughput between the three APs. And again, you'll notice each AP is getting roughly the equivalent amount of airtime and data utilization versus Ubiquity, where some APs are getting much better data throughput than others because they're fighting with each other for that airtime utilization. So those are the benefits of smart antenna. Another challenge that we run into a lot is, again, as we talked about, most APs have a fixed antenna and they're designed to be mounted in a central area directly above the area to be covered. However, out there in the real world, there are times when you cannot mount these APs on the ceiling. You've got to mount them on the wall for whatever reason. So now you're using an antenna pattern that's designed for ceiling being mounted essentially 90 degrees from where it's supposed to be. So now you're sending a lot of signal up into the floor and ceiling. So one of the things Zyxel has done is we have some access points out there that have what are called dual optimized antennas. So basically, unlike smart antenna, where we've got this really cool technology that can go through hundreds of antenna patterns, we've got an AP that's got two fixed antenna patterns, one that's optimized for ceiling, one that's optimized for wall. So if you don't want to spend the money for smart antenna, but you know some of your APs are going to be wall mounted, you want to take a look at buying an AP that has this dual optimized antenna technology. It doesn't add that much to the cost and gives you a lot more flexibility as to where you mount these APs without having issues with the performance. So just some general guidelines here. Again, in general, most APs are designed for ceiling mount. So you're going to want to mount them as centrally as possible, and you're going to want to mount them as high as possible within reason. Obviously, if you're in, a basketball arena or something like that where ceilings are 40, 50 feet high, it's probably too high. You're going to be too far away from your clients and your signal is going to be radiating too far out and causing interference issues. But within reason, you want to mount it as high as possible. So that way the signal is going directly from the mobile device to the AP with having to pass through the minimal amount of obstruction. So by putting it high, it lets the signal, go up to the AP and can bypass cubicle walls, people walking around, copy printers, things like that. So when you're mounting these up there on the ceiling, you don't necessarily have to poke holes in your acoustic drop ceiling. Generally, most acoustic drop ceiling, tiles don't cause much absorption or attenuation of the RF signal. So if your client doesn't want you, drilling holes in the drop ceiling, and there's no issues with plenum, you can mount the APs and just by setting them on top of the drop ceiling, and they'll be able to send that signal pretty good directly through that acoustic tile to cover the area underneath them. Again, not all APs are plenum rated, so you might want to take a look where you're mounting them. Does it need to be a plenum rated device in order to be installed there or not? That's something you have to keep in mind. If you are mounting them on a physical ceiling, keep in mind that metal is the bane of RF. So you don't want to mount this, next to an air conditioning duct or between some conduit, things like that. You may want to use, if you have a ceiling that's like that, you may want to get some sort of standoff that allows you to drop the AP below metal things that might be causing interference issues for you. When it comes to hotels, the traditional way that we used to do hotels was we used to put access points in the hallway, and you would cover anywhere from 4 to 16 rooms with one access point. Unfortunately, that just doesn't really work that well anymore. So what we're seeing is most mid-tier and higher hotels are switching over to 1 AP per room or 1 AP per every other room and mounting those APs in the rooms. And that just has to do with the fact people are expecting a better quality signal. Hotel room is going to have more devices in it. Back in the day, it was just your laptop. These days, it's your laptop. You want your phone on Wi-Fi. You want your tablet on Wi-Fi. Who knows what else you may have. If you've got family or kids traveling with you, each of them probably has their own device that wants on the Wi-Fi. They're wanting to stream video and stuff like that. So the mounting the AP in the hall method just doesn't work for that. You get too many users on one AP. You've also got signal that's got to penetrate 1 or 2 rooms. Maybe it has to go through a bathroom with all the plumbing fixtures. So it's just not a good enough quality Wi-Fi connection for most hotels these days. So places, people like us and other vendors make these lower powered access points that are specifically designed for mounting on a wall plate in the guest's room itself. So that's sort of the future. I mean, if you are mounting APs in the guest room, some things to keep in mind is people like to steal everything in a hotel room. So generally you want to use some sort of locking mount that makes it difficult for someone to remove the AP from the wall. You may want to hide the AP behind something. Another key thing here is you don't want any lights on it that can't be turned off. If you're mounting it on the ceiling, you don't want a flashing green or red or whatever light up there. People get paranoid about that. It interferes with people's sleep. So you want an AP where you can turn off the LEDs. When it comes to public areas in a hotel, generally, basically segment off your hotel into different public areas and plan each individually. The hotel bar should be different and separate from the lobby, and that should be separate from the pool, which should be separate from the conference rooms, etc. So plan each of those independent of each other. And you're just going to decide, how many APs you need, generally based on the number of users that are going to be in that area. In lobbies, you generally don't have a lot of users on there, so you would space them out. In something like a conference room where you may have 40, 50, 60 people all in a small area, really good idea to look for something with like a smart antenna on it to be able to help support those number of users and maintain a high quality connection. Same goes for bigger areas like expo areas. You want to use a smart antenna to try to reduce the interference with all those devices and all those APs in one area. And you'll want to load balance those areas as well. So again, you want to plan each of those individually. You don't want to be load balancing the lobby with the hotel bar. So each of them should be their own separate little segment on your network in their own pool for load balancing. When it comes to schools, the main thing has to do with how are they using Wi-Fi in this school? How are they using Wi-Fi in this classroom? Is this a smart classroom where every kid has a Chromebook and the teacher is taking over their Chromebooks and pushing out video to their Chromebooks? Or is this just a typical classroom where they're still using an overhead projector and students don't have laptops, or if they do have laptops, they're only using them during free time for browsing Wikipedia or turning in homework assignments? So if they're, so obviously if they're just doing that, they don't need as much coverage, they don't need as much bandwidth available as if the teacher is pushing out streaming video to each individual device. So that's something to take in mind. What are they doing and how are they using that? In general, the teacher and student should be on separate networks. Use VLANs to do that, to isolate out, to make sure students can't access confidential teacher resources. For class sizes of about 20 students, you generally want 2 APs per room. If you've got 30 or more students in a room, you want to use smart antenna technology. So now let's talk a little bit about Wi-Fi 6. That's obviously the latest and greatest technology that's out there. It has also been known in the past as high efficiency wireless. And the reason for that is a big part of Wi-Fi 6 is rewriting a lot of the cardinal mistakes that are part of the Wi-Fi standard and solving these issues that have been plaguing Wi-Fi for a long time. And the high efficiency meaning that you can fit a lot of users in one area, you can fit a lot of APs in one area without interfering with each other. That's sort of been the gain there, is to solve those issues. Also known obviously as Wi-Fi 6. So the cool thing about Wi-Fi 6 here is it works in both your 2.4 and your 5 gigahertz radios. What a lot of people don't know is that, your 11AC product, the 11AC technology is only on that 5 gigahertz radio. There's been no change to the 2.4 radio. Your 2.4 radio is still an ancient 11N technology. But it's designed specifically for those high density environments. And it gives you stuff here like 1024 QAM. It replaces OFDM with OFDMA. We now have upstream MIMO, so you've now got the ability for multiple client devices to transmit to the same access point without interfering with each other, but at lower speeds. The ability to reuse spectrum, more efficiently allocate spectrum, the ability for your AP to coordinate who transmits when, all sorts of cool stuff that make Wi-Fi 6 a big game changer when it comes to Wi-Fi. Now, one of the challenges with this is a lot of these benefits of Wi-Fi 6 require all of the devices using that channel be Wi-Fi 6 devices. So it's going to be a while before we truly see the benefits of Wi-Fi 6, because it's going to be a while before you replace all of your laptops and tablets and stuff with those that support Wi-Fi 6. So Wi-Fi 6 was approved earlier this year. It's finally been officially approved, although products had been available for a good year, year and a half before that, especially on the consumer side. So you say, well, how is it they had products on the market calling themselves Wi-Fi 6 before it was certified? And there's two answers for that. One is because these products were based on an early draft and they don't actually have all the Wi-Fi 6 features. They're just calling themselves Wi-Fi 6 for marketing. Although towards the end here, Wi-Fi 6 the standard was far enough along with some of the newer stuff, was able to launch before it officially got ratified, but was able to be updated via firmware to support everything. Which leads me to this slide. When Wi-Fi 6 is not Wi-Fi 6. So in order to jump into the market, to get product out there early, chipset vendors put out chips in the early days that supported some of the improvements in Wi-Fi 6, but not all of them. And unfortunately, a lot of companies chose to market those products as Wi-Fi 6. You might remember when 11N came out, for those of you that are old like me, they did the same thing, but people were much more honest and they advertised their product as pre-N. Not so much with Wi-Fi 6. With Wi-Fi 6, they're launching what are essentially pre-Wi-Fi 6 products, and we're calling them Wi-Fi 6. And they could do this because no one is enforcing the use of the term Wi-Fi 6. To get the Wi-Fi 6 logo from the Wi-Fi Alliance, you do have to be certified. But as long as you're not using their logo, you can still call yourself Wi-Fi 6 without any issues. So the challenge we have here is these early gen chips are missing some of the key features that make Wi-Fi 6 Wi-Fi 6. On the screen, I've got a comparison between Qualcomm's Gen 1 and Gen 2 products. Same sort of thing with Broadcom. I just don't have a separate slide with their comparisons, but it's roughly the same thing. So what you run into is you're missing some stuff on these chips and it cannot be upgraded with the software update. So you're missing the upstream OFDMA, upstream MIMO. You're missing out on things like TWT, which has to do with designating when different users and devices can transmit. BSS coloring, which allows you to put more devices into the same area without them interfering with each other, and other stuff like that. So you would say, well, that's just on the older product. And unfortunately, no, I mean, these products are still being sold as Wi-Fi 6 today. In fact, probably the largest consumer and SOHO vendor of Wi-Fi product just launched a new business line of Wi-Fi 6 APs that are super cheap. And the reason they're super cheap is they're still using this Qualcomm Gen 1 chipset. So they're missing all of these features, but you wouldn't know it because they aren't going to tell you. The best thing you can do is check the data sheet and see if some of these cool Wi-Fi 6 features are listed on the data sheet. If they're not on the data sheet, they're probably a Gen 1 chip or a Gen 1.2 chip that are missing some of these key features. Another thing that's going on is another big vendor out there, Ubiquiti. They are only putting the Wi-Fi 6 on the 5 gigahertz radio. So if you buy a UAP, what is it, AP6 Lite and the AP6, whatever the other one is, Pro, it's only Wi-Fi 6 on the 5 gigahertz radio. The 2.4 radio is still Wi-Fi 4/Wi-Fi N. It's 10-year-old technology. So just something to keep in mind, especially with the lower priced Wi-Fi 6 APs, is that they're maybe cutting corners to get the price down as low as they have. Maybe using an older chip, it may be they're only deploying Wi-Fi 6 on just one of the radios, not both. There's something else that we occasionally get questions about. It's something called Wi-Fi 6E. So the E stands for extended. So the FCC has opened up some more spectrum for us to play with. This spectrum is in the 6 gigahertz space. So Wi-Fi 6, the way the Wi-Fi 6 standard was written is you can port Wi-Fi 6 technology to any frequency. So you are going to see products out there that support Wi-Fi 6 in the 6 gigahertz spectrum. I think there may be some consumer stuff out there. I don't think there's business stuff out there. Feel free to correct me if I'm wrong. If it is coming though, and basically it unlocked a huge amount of spectrum. You might remember we were talking about, just how limited the 2.4 spectrum was, and even 5 gigahertz kind of gets, limited when it comes to non-DFS channels. So this is going to allow us to use 7 160 megahertz channels without overlapping. 5 gigahertz only allows us to use 2. So it's a lot more spectrum. It solves a lot of the issues we have with co-channel interference. But as we talked about earlier, as frequency goes up, range goes down. So you can expect range to be less. It's also going to take a lot of time before many client devices support 6 gigahertz. So you may be able to go out this fall and buy yourself and deploy Wi-Fi 6E access points, but it's probably going to be years before the majority of your users have products that support 6E, because it drives up the price, right? You have to have different antenna, right? You have to have an antenna that supports 2.4, 5 gig, and 6 gigahertz. So it drives up some of the costs. The chip itself is physically larger. You've got to have amps in different frequencies. The other challenge is just like when they opened up 5 gigahertz, is there's already people using this spectrum. 6 gigahertz is what mobile news reporters use to stream their video. Utility companies use that for smart utility stuff. So instead of DFS, they have another technology called automatic frequency control that's should be similar to DFS, but it should be a lot smoother and easier to use with a lot less disconnections than 5 gigahertz DFS channels. So it's a really cool technology. It's really neat. It's great that it's coming. And you should start seeing these products popping up more and more towards the end of the year and early next year. Zyxel will at some point have some 6E products. Those absolutely are being worked on. A lot of it right now just has to do with when the chips are going to be available. And it's going to be the same as it's always been for any Wi-Fi technology. The first chips are going to be missing some features. They're going to be aimed more at the consumer space. It's going to take a little while for chips with the advanced business class features that people are looking for to hit the market and to get stuff run out. So it will be coming from us and from others. And also just something else to keep in mind is it'll also sort of add some confusion because not all products that support 6E will have 3 radios. Some of them will only have 2 radios, and you'll have to decide which of the 3 bands you want to support. Do you want to support 2.4 and 6? Do you want to support 5 and 6? Do you want to support 2.4 and 5? Only some will support all 3 bands at the same time. Again, just because of cost, right? You need 3 different radios, 3 different sets of antennas, and you need a processor that's able to handle the throughput on all 3 of those. So anyways, guys, that's it for today's webinar. I hope you found it beneficial. If you have questions, again, send them in using that question and answer interface. I know I'm not always the best at explaining these things and making these things clear. So, feel free to ask me to clarify some of this, and I'll do my best to do it. I have been asked here to share with you guys, we've got our YouTube channel, Zyxel America channel. doesn't exactly roll off the tongue, but most of our webinars will get uploaded there, so you can watch those at any time in the future. If you had people you thought might have found today's webinar or one of our past webinars interesting, go to our YouTube page. They normally get posted there within 1 or 2 days. And most of these webinars we do the same webinar every month or every 2 months. So even if today's isn't up there yet, probably the last time I did this webinar, it's up there for you. And then also, feel free to add us here on LinkedIn, where we are Zyxel US channel. And the reason we're focusing on channel here is because we have split the company between what we consider channel business, which is VARs and system integrators and end users, and service providers. Guys like CenturyLink and Verizon and stuff like that. They're two different markets, so we've sort of split things off so we can tailor the message to each. And then just also here, while I'm waiting for some more questions to come in, looks like I've got one. Just to highlight here, we do have user forums, forum.zyxel.com. A lot of announcements, security related, new product announcements are announced there first. That's a great place to find them. It's a place where if you're having issues or questions and you don't need immediate help, you can post it there and get help from your other users. And then on top of that, that forum is actively monitored by both our HQ tech support and our HQ product managers, and they will occasionally answer questions, but even if they're not responding to you, they are absolutely monitoring that forum for feedback, ideas, things that aren't working, stuff like that. So it's a great way to, get your feedback directly in front of the people that can, take that feedback and do something with it. And then my email is up there on the screen, seanr@zyxel.com. Feel free to reach out to me offline with stuff. Feel free to give me suggestions for other webinars you'd love to see me put together. We do these to give you guys some benefits, and we need your feedback on what sort of information you'd like from us that you would find beneficial. Nothing sucks worse than spending a couple weeks putting together a presentation and we only get 3 people to join. So we need your feedback as to what you'd like to see us presenting, what you would find valuable. Okay, so now on to questions. This is from James. Oh, he just said great expectation or explanations. No question there. And then Marcus, can you slow the slide with the drop in signal to the walls and tinted windows? Sure. Let's pull that up. Give me just a second. So Marcus is asking to see, whoops, this slide here. So there we go. So this is just giving you a rough idea of how much this stuff is dropping off. Phil is asking about downloading this. So again, the video version of this will be posted to our YouTube. We could probably send you a PDF. Reach out to your salesperson. I'm assuming you're one of our VAR resellers. So I'm not sure who you work with. It's either going to be Jacob, Andy, or David. Just reach out to them and say, hey, can I get a copy of today's presentation? And we can probably get you a PDF version of it for you to check out. And I don't have any other questions. So I'll stick around for another minute here to see if maybe somebody's working on something. But otherwise, thanks for joining us, guys. I appreciate you taking your time out of your day to listen to me talk. Hopefully you found some benefits to this. And again, if you have ideas for presentations, in my case, when it comes to wireless, when it comes to Nebula, when it comes to consumer stuff, drop me an email. Let me know what information, what you'd like to see us put together, and I'll see if we can't maybe put together a webinar on that. And of course, you can always reach out to your salesperson if you need some specific training for your team on a particular topic or something like that, or you need some help from our sales engineer to help you figure something out. Your salesperson can arrange that for you. And doesn't look like I'm getting any more questions, so I'm going to go ahead and end today's webinar. Again, thanks for joining us, and I'll see you at the next one.